So today I'm going to prove the following theorem. This is basically the particular case of Fuglede's theorem applied on a finite complex inner product space, sometimes called a Hilbert inner product space. So what do we have here? We have two linear operators T1 and T2, which belong to the finite inner complex product space, as I mentioned. And then they commute between each other. And it is also given that T1 is normal linear operator. So we need to prove that T1 commutes with adjoint of T2 like this. So here's what I'm going to do first. Given that T1 is the normal operator, there is a well-known fact that there is a diagonal representation of this, which is defined as T1 matrix representation of T1 with respect to the basis S. That being said, there is such a basis S, which belongs to the space of basis of inner product space, which is defined the following way. This is the orthonormal basis of eigenvectors. That being said, that we have inner product equals to a Kronecker symbol. This is the orthonormal space, orthonormal basis. And this diagonal representation can be given as essentially there exists, this is equivalent, there exists the matrix P, right? What is matrix P? Matrix P is the change of basis from S to a standard basis, such that D equals P adjoint and then T1 with respect to the standard basis P here. And what is important here is that P is essentially, um, unitary matrix, which is unitary. So what does it tell us? Well, it indirectly points to the fact that our D can be represented as a diagonal matrix. And this is a well-known fact that this diagonal matrix is actually represented by eigenvectors. By definition of eigenvectors, we can rewrite this like that, by definition. And then let's define a commutator between T1 and T2 adjoint. I'm going to define a commutator T1 and T2 adjoint. By definition of commutator, that would be T1, T2 adjoint minus T2, T2 adjoint T1. Consequently, the proof statement or hypothesis is equivalent to commutator equals 0. Since it was given that this complex inner product space is finite, meaning that it has a finite dimension, the problem is pretty simple. Let's do the following thing. First of all, it was given that T1 and T2 commute. They're identical by definition. And let's try to take a look. What is the ij element of this matrix multiplication? The ij element of the matrix multiplication here is, by definition, lambda, which is the eigenvector T2, which is ij. And you know, T2 is actually Bij, for example. This is not necessarily diagonal matrix. It should not be diagonal. It could be any matrix. And T2, T1, Ij at the same time is essentially T2, Ij multiplied by lambda j. Therefore, the difference of these elements, Ij minus T2, 1, Ij equals 0. It comes from here, from this fact by definition, right? And then we can say that it is equivalent to saying eigenvector I, T2 Ij minus T2 Ij lambda j equals 0. And then because T2 Ij belongs to the, complex scalar space of scalar values, we can conclude that I lambda j lambda I minus lambda j, we can factor out this value essentially, Ij equals 0. And what happens here? What can we kind of deduce from this equation? We can deduce that if I lambda I equals lambda j, that means that, well, this equation holds. So let me just simplify that. From this expression, from this equation, we say that either lambda I equals lambda j, or, this is not exclusive, it's just or, T2 Ij equals 0. And one more important thing here, you will see why it is important. We'll get to this soon. So T2 Ij equals 0, right? No, let me just use lambda for this purpose. If lambda I not equal lambda j, this is the equivalent lambda I minus lambda j not equal 0, which means that lambda j minus lambda I is not equal 0. And that essentially means that T2 gi equals 0. So we just commuted them. Right. And that also means that conjugate value of T2 ji equals 0. Well, step number 4. So the next thing that we have to do here is to show the commutator, how does commutator look like? How does individual element of the commutator look like? So we have T1, T2 adjoint minus T2 adjoint T1. And let's see, how it looks like. So you can find Ij here. Well, that's essentially T1, T2 adjoint Ij minus T2 adjoint T1 Ij, which is by definition lambda I T2 adjoint Ij minus T2 adjoint Ij, right? Times lambda j, which is the same, which is equivalent to lambda I T2 gi conjugate, because adjoint is the conjugate transpose, and T2 gi conjugate value here, lambda j. Again, we can factor this value out, and we have lambda ij minus blah, 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 and conjugate transpose value T2. And here we can see that if lambda I minus lambda j is not equal to 0, then as was shown before that, as was shown above, Here it is. T2 conjugate transpose equals 0. Otherwise, if I equals j, that means T to ji conjugate lambda I minus lambda j equals 0. And in this case, it also equals 0. Here it is. So in both cases, it equals 0, which means that our commutator equals 0 too. That means our commutator equals 0. And that's basically it. That's the proof of this theorem.